Hello, hello. Good morning. Can anyone hear my voice?
Yes, aloud.
Okay. Okay, so I think shall we start? Since I try to finish the discussion within 4 weeks, right? And after that, before the end of this November, we're gonna have the small exam, right? To get the score for grading. And I think it's not so difficult. I already provide you some previous exams so that you can have the idea about the what's gonna happen with the exam room and with the COVID-19 situation. We're gonna have the something like the online exam, so it take not so much stresses over you, quite not so difficult. So please well prepare yourself for the exam at the end of this month. After I complete the discussion, maybe the week 1 week later, we're gonna have the exam with you. Okay, let me back to the chapter of the optimizations again, where people would like to get the tool, mathematical tools. As the engineer, we need the tool like the calculator, so that we can solve some real or actual physical problems to get or to obtain the design of the buildings, design of the bridges, so that it has the, how to say, appropriate design or the most effective design or the most cheapest design, whatever you're thinking about, the optimization will come into the picture. So as the tool, we need to learn how to use it, understand how to formulate your problem to the mathematical model from the real physical world, and then apply this tool or this mathematics to help you get the solution. One of the things that we already discussed is about the convexity and the concavity. This is quite important if your objective function to optimize something, you write down your objective function. And if you can write down the objective function in such a way that is well behave as the convex or concave functions, then you guarantee that your answer is gonna be the global optimality. No one can get better solution than you in this world. This is the global maximum, and it's gonna be the global minimum once you obtain the solution. Therefore, people very happy if they have the objective function as the convexity or the concavity. To classify things, to determine whether your function is a convex and concave function for one variable or just a single variable problems, is quite easy. You just perform your second derivative and see whether this second derivative or what you call the curvature is positive or negative. The f of x will said to be, oh, I lost my, oh, it's unlucky today. I lost my Surface Pen. I should write down. Yeah, if f of x is said to be a convex function, if its the second derivative is greater than 0. The thing is happen like this, right? It look like I have the convexity, the curve is like this. And you know about the slope. Right? If I find this slope of each 1, 2, 3, 4, 5 point of this curve, this function f(x), maybe you see that the slope here may be 2, 1, slope is 0, -1, -2, something like this, right? So the change of the slope is a second derivative. For the beams, we well known about the curvature. It's a second derivative as well. It's a quantity that related, directly related with the moment, section moment, bending moment of the beam. And that curvature, or the second derivative of the pink function, as you can see, is positive. In this case, your function f of x become a convex function. On the other hand, if your f of x, the second derivative less than 0, then your f of x become a concave function. And if whenever your function f of x, the double prime equal to 0, is a convex and a concave function. Come both, it's just a linear function, in fact. But if your f of x sometimes is greater than 0, I mean the second derivative, sometimes it's greater than 0, sometimes it's less than 0, depending on the value of x. For example, if your problem, you perform the second derivative, is not a constant, it's become a function of x itself, something like 3x plus 4. If my second derivative of the function f of x becomes something like this, I would say my f of x is neither concave or convex function. It's neither nor, because it depends on what the value of x you introduce to the second derivative function. If I introduce the positive number of x, of course, I got the positive value of the second derivative or double prime of f. But on the other hand, if I introduce some value of x like minus 10, minus 100, what they obtain from the second derivative of f of x which become a negative value. And this is not strictly concave or convex function. It's neither nor. Okay, so this is one of the example when you have the f of x equal to 3x squared minus x, then you obtain the double prime equal to 6 is positive number. Therefore, and for sure it's constant number. No matter your value of x is always 6. Therefore, your f of x is a convex function in this case. Number 2 is you see the double prime is a 6 of x, and therefore, if you would like to get the solution of your objective function f of x like this, and you will define your unknown is within the positive quadrant. I mean, the x become the value of 0 to positive infinity plus infinity, then you can say your problem is a convex function. But if you cannot define the positive region or feasible region like this, and you need to include all the real number of x, it means you have both x is negative and positive. And this function, objective function, is not good because it can be a concave function and it can be the convex function depending on the value of x. Therefore, the conclusion of the whole set of the real number x, you would say this f of x is neither convex nor or concave function. Seems quite easy to classify or determine whether your function is a convex or concave function in case of a single variable. But if you have the multi-variable functions, this is a case where your optimization problems contain many of variables x. You have x1, x2, x3, x4, many x, right? To perform the second derivative of the function contain many value, many variable like this is not well defined. What is the second derivative? But the definition is more or less, it's like we consider the partial derivative instead, right? Since you have many variable x. So to obtain the way to find whether your function, multiple variable functions, is a convex or concave function, we turn our interest, not consider the second derivative of the function f directly anymore. We look at the Hessian function. We consider the Hessian matrix. The matrix in which defined as the second derivative, partial derivative of the f with respect to xi and xj. In this case, the Hessian become, as you see, the slide is a matrix. The sizing is the number of variable. It's a matrix n by n, square matrix, symmetry matrix. The sizing is n by n. Depending on the number of variable x you have. If you have 4 variable, like you have x1, x2, x3, x4, therefore the Hessians of your f function f of x become the 4 by 4 matrix. Okay, the way we look at this Hessian and define whether your function f is the convex function or concave function, we look at what they call is the leading principal minors. Leading principal minor. If all leading principal minors of the Hessian matrix H are non-negative, then your function f of x is a convex function. And if, there's a little bit different, non-negative. But if the leading principal minor of H and H is non-negative, but more than non-negative, you can find any number of them are all positive. It means you have no zero. When they say non-negative is something like this, right? Greater or equal to zero is non-negative. But when we say positive is something a little bit different. That means I cannot contain any zero value in my leading principal minors. This is a positive, strictly positive. And then therefore your function f is not just a convex, but it's now strictly convex. Before it's just a convex function, but this one, if your leading principal minor are all positive, then your function f is strictly convex. The difference is when I have just a convex function in many, multiple variable case, it look like my function is like this. If I draw it, actually it's a surface, it's many variable, right? I cannot draw the function in just the line drawing. It could be the surface or maybe more than that. But to make you feel the difference, I would like to draw a function like this. U and V. In the above, the non-negative leading principal minor, it looked like I contain some zero within my leading principal minor. Therefore, even though I can get the global minimum, but it looks like it's not one global minimum. It's something like you see many point of this are all the minimum value. But if I have a strictly convex function, it looks like I have only one, maybe I would say one global minimum. Actually, global minimum should have one, right? In the definition, when we say global, mean no one is greater than or better than me. But it seems like if my function is convex, not strictly convex, just convex, the case number one, we are talking about case number one and number two, right? Case number one, even though I can find the global minimum, but it's not guaranteed that my solution has a unique one solution. Maybe I can find another location that has the same amount of the objective function or the optimality. But for the strictly convex, it's much better, where it's guaranteed that the solution I obtain is only one solution that can satisfy my objective function, and that is a global minimum point. Similarly, for the how do you say the case of the concavity, where when we look at the leading principal minor of the H and H, you have to look at the sign of the -1 power k. If the k leading principal minor of H had the same sign as the -1 power k or 0, then f of x is concave function. This is case number 3 and number 4. Let me say so. Number 4, if I contain non-zero, then my function becomes the strictly concave function, and I have only one global maximum. Guarantee that I have only one global maximum. Okay, for the solution of number 4. So this is just the definition where we can determine whether your function is a convex function or concave function. let me look at some example before we ask you on the quiz for today. If I have a function f of x equal to 2x1 square plus tx2 square plus 4x3 square minus 8x1 minus 12x2 minus 24x3 plus 110. I would like to check whether this function multiple case, right? You see, you have the three variables in total that are x1, x2, and x3. The first term, I believe I got this from with respect to x1. And the second term is the partial derivative of f with respect to x number 2 and with respect to x number 3. Okay, so you got something like the gradient or grad of f of x equal to 4x1 minus x, 6x2 minus 12, and x3 minus 24. Okay, from this, if you perform one more derivative, remember Hessian is a second derivative. To perform this one, I believe 4 is come from this, right? With respect to x1, with respect to x1, something like this. And you can obtain 0, 0, 0, 6, 0, 0, 0, 8 as the Hessian matrix. When you obtain the Hessian matrix like this is a constant matrix. We calculate the leading principal minors of this Hessian. The way we do is to find the determinant of the H1. When I draw the determinant of the first corner, I mean the left, up left, right? We go from left to the right, upper to the lower. Okay, so I got 4, I got 24, I got 192. Okay, 4 is easy, right? But this one, if I remember correctly, you got something like this, right? You multiply the diagonal term, you got the minus 0, you plus 24. But this one, I believe we have learned this from the high school level. It could be something like a 0, 6, and 0. And then you got minus here is all 0. Got there, I think you got plus 22 and plus 0, something like this. That's why you finally obtain plus 192 as a Hessian number 3, leading principal minor number 3, right? So you see the leading principal minor of the Hessians becomes all positive number. 4, 24, 192 of them as positive number. Therefore, I can make a conclusion that my f of x is the strictly concave function. And the local minimum, when I obtain the solution, gonna be the global minimum for me. And this is very good. It's guaranteed that I can find only one local minimum, and that local minimum, in fact, is just the global because it's only one in the function. Okay, you cannot find any other location or point or position that can or solution that can provide minimum value. I mean, smaller value than mine. Okay. The next example, you see, we do the different function f of x, and once we calculate the Hessians, we found that the leading principal minor is 2 minus 5 minus 2. Okay, of course, when you have the minus sign in the leading principal minor, it cannot be a concave function. It cannot, I'm sorry, it cannot be the convex function. So what we will consider is about the sign convention of this, whether it's a minus. It's gonna be the concave function if, in the definition, right? If your sign convention is something like this, minus 1 power k. This is k. This is k. So the first term, I would like to have minus. The second one is the minus 1 power 2, it should be plus. And the third, it should be minus, right? But what we obtain from this example is not like this. Is plus 2, is minus 5, and is minus 2. So it's a plus, minus, minus. It's not like a minus, plus, minus. Therefore, the conclusion is my f of x is neither convex nor concave function. Okay, it's gonna be the concave function if you have something like the first Hessian you have minus 2, the second, I'm sorry. The second you have plus 5, and the third you have minus 2, something like this. If you have the leading principal minor as minus 2 plus 5 minus 2, then you can say this is a concave function, and strictly concave function since they contain no zero. Okay, but in this case it's not. Therefore, the conclusion is correct, saying that this f of x is neither convex nor concave function. Okay, before we go further, I would like to check your understanding here using the quiz. So I don't know, I will send you, you can open the Line application, right? Maybe I will send the link into the Line application because maybe to the chat. Let me try to get this for you. Okay, the quiz that I will use with you, maybe some of you already know about the Padlet. I use the application Padlet. Therefore, maybe we will a little bit learn about this together. The Padlet is very simple. Let me try to show you some. Okay, I will stop my sharing here. And maybe I will use another account to share with you to show you the Padlet. Okay, this one. Okay, I will use this dashboard to ask you some questions, small question, and let you have like 5 minutes to solve the problem and return me the answer. For example, in this case, the example I show you, I will provide you the link. I think they're gonna be the link. If this one, I will share with you. Maybe copy the link. When I copy the link, I will share you in the chat. Hope you can use the chat. It's the chat window. Oh, I could not find the chat window. Where is it? Okay. If I send this chat to every one of you, look at the chat window. You can have the link, right? And I hope if you follow the link, it's gonna be something like this. You will have to provide me the subject and write something, your answer. In this case, for the subject, you have to write down your ID, right? For example, if I write down my ID, let me try to show you maybe 111111. 821. This is my ID, and my answer is if I try to write down some answer like x1 equal to 25, and then press enter, x2 equal to 26, and then I just submit. I think in your case, it's not the publish. It could be something like a submit. Okay, when I say submit, it come to the dashboard of mine. That's it. This is already the example. For example, my answer is 25. I'm sorry, 15 for x1 and 76 for x2. And I put my ID on top, and then the answer at the below. This is complete my quiz already. You just wait for me that, okay, the time is up. So everyone, you stop sending me the board, the answer. Okay. So it look like, okay, some of you might want to try. If you want to, you can just try to write down something, right? Many of you connect now, 7 of you. You can try to submit me the answer, your ID, if some of your friends can do. Please. This just want to practice that you can use the Padlet. Okay. Another ID come, you see, is your friend. Is okay. In your case, because you are not the owner of the Padlet, you will have something saying that like waiting for approval, right? Okay, just feeling that your answer is come to me already. You see that the board. I will keep looking at this dashboard and see the answer from all of you, but you cannot see each other. Later on, I will not open this and share this screen to all of you, so you cannot see others. Okay, any problems? You see someone just write down the answer like this is not okay, right? You have to put your ID first. So the first line is your ID. Put your ID and then the answer. Okay. It look like and when you finish, suppose you already finished and the time is up, I will close the chat. Something like this. I will leave. I will come to the change privacy, and then I said private. I will lock everything, right? After I enter save here, you cannot modify your answer anymore. Okay, let me save. Yeah, and I hope it will lock. And from now on, you cannot modify or edit your solution. Okay. So it's not so difficult, right? Let me try to quiz you. One question, Leo quiz. Now, about the hedges. I would like you to calculate the hedging for me, but maybe this could be something like we stop sharing here. Going back again to this one. Okay. I will try to ask you about the check of the function f. Okay, let's quiz with this one. This function f, let me draw you another function, 3 variables again. Let me type with this one, 2x1 squared plus, I'm sorry. I will modify the bit, the function for you. plus 3x2 square, but it should be changed to 6x number 3 square plus 2x1 x2 plus x1 x3 minus x 2x1 minus 5x3 plus 20. Okay. Please check this function f of x, whether it's a convex function, concave function, strictly concave function, strictly convex function, or neither nor. Okay. You have 5 minutes. I will start to create a Padlet for you and send you the link very soon. Okay. You have 5 minutes to thinking about this. We already start, okay? You start, get the solution from now. Just find whether this function f of x is a convex function, concave function, or none of them. Okay, I already sent the new link of the Padlet, right, to all of you in the chat. So you can follow the link and answer me whether this f of x is a convex function, concave function, strictly convex, strictly concave. Okay, same. I got 2 answer from your friends already now. 3, very fast, very good. Okay, good. Starting with your ID, right? And then below you write down for me strictly convex, strictly concave, something like that. Okay, I got 8 of you. 9. There is one student just write down h number 1 equal to this number, number 2 equal to that. I don't care, right? Write down your ID. Don't show me the leading principal minor. I don't want to see. Just your ID because I will check your score. ID and then the conclusion. There's one student still don't understand yet, maybe. You have to provide me your ID, I would say, in the first line and then the answer. Good. Okay, 1 minute more. I need the conclusion as well. Some of you just provide me the H1 equal to this amount, H2 equal to this. I don't care, right? What I care is the conclusion, whether it is the convex function or concave function. Strictly convex, strictly concave, that's it. No need to provide me any detail more than that. Hurry up. You have only 1 minute left. One, 2, 3, 4. I got maybe I already obtained just 21, 22 solution now. It seems some of you cannot connect to the answer yet. Okay, I will count down 30 seconds. 10 seconds. In your display, maybe it shows something like a waiting for approval, right? It's normal. Don't be worried. Okay, I think it's time up and I will try to stop sharing. Okay. Let me share with you about your solution of obtain form of views like this. Maybe I share the screen to show you that your answers come. Don't be worried. Like this, right? Oh. next time, right, you don't to waste your time to write down too many information here, right? Just the answer like a strictly convex function here, that is enough. I will check this. So I hope you can see your answer and your friend's answer now. It looks like you can get the right solution. They say the strictly convex. The answer would be strictly convex. I will check and confirm you again because some of you say just a convex function, not strictly convex function, and some of you say it's neither convex nor concave. But many of you say strictly convex function. And I think it would be this answer. Okay, never mind. You check yourself, and if you found that the strictly convex function is not true, you can challenge me. Okay. Let me go back to the chapter again. So we now consider about the procedure or the protocol we use for obtain the solution of optimization. Previously, we just define a function, we define the Hessians, define the convex and concave, but its application is not well defined. How to apply the convexity, how to apply the concavity. But right now, we will start with a very simple case where the single variable optimization is concerned. I think you can recall your knowledge about the high school level, or this is the same, where for the optimization, you need the two conditions. One is called necessary condition, another is a sufficient condition. The necessary condition is a condition to confirm that you already obtained some candidates of the optimality. The candidates of the optimalities is determined by looking at the slope, the first derivative. And in the case of a multiple value case, we call that stationary point. The point that is very stable, slope is zero. This is a necessary conditions. Once you obtain the necessary condition from the whole set of the X in the feasible region, you have infinite many number of the candidate of X, in fact, from the beginning. But when you apply the necessary condition, you will obtain only some set of X, some set of the variable X that can be the candidate for the optimality. Okay? And from that, we will go further to check which candidates is the optimum one. Is the real local maximum or local minimum or global maximum or minimum by considering another condition called sufficient conditions. In the sufficient condition, the whole set of the candidate will come to be checked by this condition, whether it's the minimum point or maximum point. Okay, we will not check the whole set of X. We will check the sufficient condition only the candidates of X that pass the check of necessary condition. See, the step is something like you have to perform necessary condition first and then coming with the sufficient condition. You cannot go with the sufficient condition before, because we need to know this the set of the candidates from the necessary condition and then check the whole set of the candidates, which candidate is the best by looking at the sufficient condition. Okay, in the sufficient condition from the single variable optimization, we look at the double prime, right? The second derivative. If when I introduce, in other words, I would say after we apply the f prime of x equal to 0, you will obtain the set of x star. The set of x star is the location where the slope is 0, right? From the necessary condition. And then I will strictly, I would say, if double prime of x star, only at the x star will be evaluated. And if the some x star return the second derivative greater than 0, I would say those candidates of x star is minimum point. And if the double prime of x star less than 0, I will say those candidates are local maximum point. And among them, maybe you can have one of them is the most maximum. This is a global maximum. And you have to compare, right? But if the candidate, imagine if the candidate, you have only one candidate, x star has only one value. It's easy because if the sufficient condition on that x star saying that this is the minimum value, your conclusion will be the global minimum because you have only one x star. It's easy. This is a case of convexity, right? Because you have only one condition x star, and that is a global minimum point. Okay, let's go further for the example. I have to step very fast. This one is easy, right? F of x equal to x squared minus 6. Okay, we got the f prime of x equal to 0. And that means you have the x star only one point and is occur at 0. X star equal to 0. And we perform the double derivative of f with respect to x. We obtain the f double prime equal to plus 2. No matter your x star is a constant plus 2. And this is greater than 0. Therefore, your x star is the minimum point. Okay. Another example, when f of x equal to x power 4 over 4 minus x power 3, we perform the necessary condition. We obtain two candidates of the x star, that is 0 and 3. So we have to check whether 0 and 3, which one is the minimum, which one is the maximum. And I think, okay, this is a necessary condition, right? Necessary condition. If we go to the sufficient condition, I think your f double prime of x becomes something like a 3x power 2 minus 6x. This is a function of the second derivative, right? And if I introduce x equal to 3, maybe I can have the positive or negative number. Okay, number 3 is easy, right? If we introduce x equal to 3, you obtain, it should be 27 minus the 18, right? So it's a positive number. So this one is the local minimum. I'm sorry, positive is maximum, right? Or minimum is correct. Okay, your x star equal to 3 provide you the local minimum value, local minimum point. But when we introduce x star equal to 0 to the sufficient condition, we found f double prime still 0. So it's very hard to define whether this point is a maximum or minimum or just an inflection point. To do so, I believe that, okay, we look at some example about this. This is the local minimum. In fact, it's occur at the x equal to 3, right? This is a local minimum, and it can be a global minimum if you can consider the whole set of the layer of x, maybe. But this one is not guaranteed yet because it's not a convex function, right? However, it's very difficult to identify whether when x star equal to 0, this point is the local minimum, local maximum, or just inflection point. In this plot, I think it can be concluded that inflection point from the plot. But be careful when you look at the plot and say something about this, that look at the plot, it could be that inflection point is not the minimum, it's not the maximum, just the saddle like this, the inflection, right? But in fact, it's very hard to say. So because if I zoom in this block, if I zoom into this block, maybe the curve is like this. You see what I mean? It's going like this. In this case, it's not an inflection point. It's the local minimum and local maximum. Therefore, considering the optimality by just plotting only is not sufficient. You need the mathematical proof as well. By looking the plotting, maybe it's very difficult because I don't know how much I need to zoom in to see something like this, to guarantee there is no inflection point or no local minimum or maximum point in my plotting window. Okay. This is a case of minimum point. It's quite straightforward. It's maximum point. How to classify the stationary point is another issue. This is the sufficient condition after you obtain double prime equal to 0. That is the way that we talking about. This is the sufficient condition. Right? We use the necessary condition to determine the candidate, the location that would be the maximum or minimum point in your domain of interest or in your feasible region. That is about the necessary condition. But after you obtain the stationary points from the necessary condition, what you have to do is to classify all the candidates, whether or which one is the maximum, which one is the minimum. To do so, you need the sufficient condition. And this is the same thing with this subject, how to classify the stationary points. The way that we mathematicians used to define this, they used the idea from Taylor series. This one, Taylor series. They just look at the function at stationary point and perform derivative, assuming that the first derivative equal to 0. This one is necessary condition, right? This one is not the assumption. This is the fact, because if you say your cell is an X star or stationary point, you have to already pass the necessary condition check that guaranteed at least the slope evaluated at X star need to be 0. This is about the necessary condition, and you have to pass the necessary condition before you can call yourself stationary point. Okay. However, in equation number one, not only the f prime at x star equal to 0, you will see that f double prime, f triple prime, f n minus 1, I mean the derivative order n minus 1 also equal to 0. And the first non-vanishing derivative is happen at the order n, where derivative order n evaluate at x star of a f function is non-zero. This means this term is not equal to 0. It can be any number, any value, but not 0. This is about equation number 2. If we have the assumption like this, you can write down what we call the Taylor expansion. The Taylor expansion is trying to estimate the value of the function close to the location that well defined. For example, if I define my function f at x star equal to this amount, and I would like to estimate what would be the function f at x star plus small variation h. You see, it's small h. You modify the variable a little bit. They want to see what gonna be the value of the f of x star plus, plus h, small h. From Taylor expansion, Taylor series, we found that the f of x star plus small h equal to f of x star plus the first derivative of f prime x star multiplied with small h over 1 factorial plus the third term is f double prime s square over 2 factorial, and plus you can imagine f the third derivative, right? Multiply with the h power 3 over 3 factorial, something like this, and go until f order n evaluate at x star derivative order n multiply with the small h power n over n factorial and plus the residual term. Okay, the order become higher and higher. However, since from equation number one, you see the first derivative need to be 0. This term is 0. Therefore, the whole term becomes 0. This term also assumed to be 0. Look at this. Equation number 1. So it seems like until the term f n minus 1 is all 0, except this. This term is the first term that become non-zero. Therefore, the equation number 3, if I put number 3 here, equation number 3 can be estimated as equation number 4, in which the difference between the f of x star plus h subtract or minus with the f of x star equal or approximately equal to f derivative order n of evaluated x star multiplied with h power n over n factorials. You see, the residue is something like if this one is order, order n, this one is become something like one more order, like I don't know, if this one is power minus n, this is 10 minus n plus 1, something like this. Smaller and smaller. In terms of the advantage of the Taylor series is that the term, if the small h is very small or small enough, you can expect that the term behind is smaller than the term before. Okay, so the term of order n factorial is much larger than n plus 1 factorial, something like this. Therefore, the sign, if you look at the sign convention, the whole term of this, the sign is the same as this. It could be have the same sign with the first term. Okay? Because the first term, the amount is quite large compared with the second term. One order is mean 10 times larger. Therefore, the sign of the whole set of the remaining terms, including the residual terms, is controlled by just the first term of the f order n. Okay, that's why we can approximate the sign accurately with the equation number 4 like this. If this the case, equation number 4, you can have the conclusion like this. If the n is the even number, then if f n of x star greater than 0, x star is the local minimum. And if n is even number, if fn less than evaluated x star less than 0, x star is the local maximum. And 2, if n is the odd number, x star is a just inflection point. Okay? Why it can be concluded like this? Maybe I would like to pay attention here a little bit, because you will use the same understanding to expand the idea for the multiple variable case. So it's quite important here. Look at this equation number 4. Maybe I can do with, okay, let me draw you a convex function. Okay, look at this. This is my x star, because this one, the slope is 0. This is my x star here at the bottom of this volley, this function. I modified a bit this function. Remember, this one is f evaluated at x star. Okay. This is your x, this is f of x, something like this. And if I look at the location x star, I can find the value of a function f, and that is f of x star, okay? And it happened at the bottom of the volley. See, if I move a little bit to the right, this is number 1. It means what? It means I put evaluate here is my f eval x star plus h, small h. See, I move to the right hand side. If I subtract number 1 and number 0, remember this point is 0. Number 1 and number 0, you see the value of number 1 is a little bit higher, right? It's higher than 0. Therefore, the subtraction of this term become positive number. Similarly, if I go to the left hand side, look at number 2. This is the f of x star minus something, right? Minus some delta. Let me use the delta, it may be better than h. Minus some delta x. I obtain number 2. The subtract of my function f of x minus delta, subtract with f of x, the same thing. You will obtain a positive number because number 2 is a little bit higher than 0, right? So you obtain positive number as well on the left-hand side of equation number 4. So this is the case of what? The case of minimum value. No matter you move to the right or no matter you move to the left-hand side from the x star, the subtract of the new position, I mean the new function f with the original position f of x star will always return positive number. You see, whether you move to the left and to the right is higher than my location, my original location 0. This is a case of minimum point. And to guarantee that, in equation number 4, you look at the right-hand side. On the right-hand side, if n is even, n mean n is the number like a 2, 4, 6, something like this, right? In factorials, always positive number. This one, no matter number is a positive number. It's always, it's integer, factorials. Positive number. H power n need to be a positive number as well because the even number is always return positive number for h power n, right? No matter you move to the right hand side, that your delta or your h is positive or negative. Your small h can be positive if you move to the right hand side. Your small h can be negative number if you move to the left hand side. But don't be worried because this power is the even number. Therefore, it returns positive number. You see, so the remaining is this. The remaining term is the pink term. It depends on the pink term. If my pink term is a positive number, the whole set, I mean the whole term of the right-hand side is always positive number. And therefore, the conclusion is minimum point. That's why you see if n is an even number and if your pink term is a positive number, your x star is the local minimum. No matter you move to, you check by moving to the left and to the right, you see you a little bit higher than the original position x star. Therefore, this is the minimum point. At x star is the minimum point. On the other hand, if the same thing, but the pink term is a negative number, it means what? It means when you move to the right-hand side and you move a little bit to the left-hand side, you still have negative value of the difference between f of x star minus plus h minus f at x star. This is the case of what? This is the case of the maximum value. The case of maximum value is something like this, right? You can imagine the pink curve again. This is your original x star. You see, when you move to the right or to the left, the function will return you some value smaller than original, than the f of x star. So the subtraction of equation number 4 of the left-hand side term return negative number, always negative number, no matter you move left or right. Okay, so this is why you have the conclusion as this, local maximum. But if In your case, n is an odd number, like a number 1, number 3, number 5, something like this, right? It's an odd number. In this case, it look like when I move to the left and I move to the right, the sign convention change. This is a case of inflection point. You see, if I move to the right, I go a little bit downhill. And if I go to the left, I move a little bit uphill, right? So the difference of the left-hand side term will change sign convention from positive to negative. When I go left, it's positive. When I go right, it's positive, something like that. It changed from positive to negative, and that is because your n is an odd number. Okay, please try to make yourself understand about this equation number 4 so that you can extend your idea into the multiple variable case later. Okay, so this is what I would like to discuss about the single variable case. For example, I'm sorry. If your function is a x power 4 over 4 minus x power 3, right? You have the two candidates for necessary conditions 0 and 3. And since your stationary 0 and 3, you have to go further to check the sufficient condition. And for the sufficient condition, it's found that the second derivative when x star equal to 3 equal to 9, that is greater than 0, n is even. Therefore, your conclusion is a local minimum for x star equal to 3, that is 5. Then when you go to f double prime of 0, x star equal to 0, you found yourself that the second derivative is still 0. Then you go further to the third derivative. When you go with the third derivative, we found that is non-zero term, is the minus 6. And since the n is 3, n is 3. Therefore, it's an odd number, and it becomes the inflection point. That's it. This is about the single variable optimization with the constraint. Saying that you have the constraint like this, x from 0 to 10 only, that within our interest is within our feasible regions. F double prime you obtain z equal to 0, you found x star equal to 1, and this is still within your feasible region. So it's quite okay. The second derivative f double prime is equal to f double prime is equal to 2. You see it's greater than 0. Therefore, the x star is a local minimum. Okay. However, we evaluate at the boundary. At the boundary, we found something like f at 0 equal to 1 and f of 10 equal to 81. Therefore, we can make a conclusion like this, that the global maximum is occur at the boundary at x equal to 10, and the global minimum is occur at the x equal to 1, right? Yeah, x star equal to 1. Second example, maybe you can play around, right? I will skip this one, quite straightforward. Look at the multiple variable case. When we extend our knowledge from the single variable to the multiple variable case, we found some difficulties because the derivative is not well defined in the multiple variable conditions. Therefore, we have to use the gradient. We have to use the Hessians, right? The necessary condition for the multiple variable optimization is very similar to the single variable, but instead of the f prime, you use a gradient. The grad of f of x star equal to set of zero, a vector zero, a zero vector. And the sufficient condition is defined as in number 1, number 2, and number 3. It said that if the Hessian of x star is a positive definite, then x star is a local minimum. And if the Hessian of x star is the negative definite, then the x star become a local maximum. And if your Hessian evaluate at the x star is indefinite, then your x star is just the saddle point. It looks like the inflection point. It's neither nor minimum nor maximum. Okay. It is noting that the symmetry matrix Hessian H is said to be a positive definite if the Q equal to V transpose HV is a positive for every vector V that is equal to 0 if and only if V equal to 0. So this is the definition of the positive and negative definite, and I hope all of you already understand about this. For example, if we're talking about any V, right? A matrix A, for example, you can find any vector V, non-zero vector V, pre-multiply and post-multiply with a matrix A, and is returned. Remember, if A is a n by n, let me use the big capital. N by n, V is a n by n, n by 1 is a V transpose, right? And V itself is a n by 1 by n, then you get just the scalar 1 by 1. This is just scalar value. If this product always return positive number, no matter you change your vector V, you can find any vector V in this world, pre-multiply and post-multiply with your A matrix, and is return always a positive number, then we call A a positive, right? If it's something like this, we say A become a positive definite matrix. Something like this. And it's quite easy to prove for a very simple matrix A like this. If my A, for example, is the, the identity matrix I, right? It's a 1, 1, 1, 1, 1 in diagonal term. In this case, you see your V transpose A V equal to this, something like this. And it becomes, I think, a summation of the VI square. Okay? And this is always a positive number. Therefore, identity matrix is a positive definite matrix. For example, it's like this. Similarly, for the negative definite matrix, is defined in the different way, right? In the opposite fashion. And if sometimes sum of V, even though V is not 0, returns 0 value of the product, then your matrix A becomes something like a semi-positive definite. For example, if I say so, sum of V return zeros and many V return positive number, then my A become semi-positive definite matrix. Okay. A positive and negative definite matrix can be checked also by using the leading principal minor. Let's come again, right? Leading principal minor that we have we used to check what they call is convexity and concavity. Remember that? Okay. If you are checking by using the leading principle minor, you will have the conclusion. You have two conclusions. One is that your A is the convexity. Okay. And another conclusion is your A is a positive definite. As a result, you can get both conclusion from the leading principle minor check. But if you don't want to do so, you use the eigenvalue. You're using eigenvalue. The eigenvalue will do with the positive definite. Very simple and straightforward. Just say something like this. If the matrix S is a positive definite, if and only if all its eigenvalue are all positive. And if your eigenvalue is negative, your matrix S become a negative definite. And if your eigenvalue, some of your eigenvalues is 0 and many others, the remaining others, the positive, your matrix S become a semi-positive definite. So it's quite straightforward, okay? Look at this example. If your function f is x1 squared plus x2 squared plus x1 x2 minus x1 minus x2, the gradient of f is the 2x1 plus x2 minus 1, 2x2 plus x1 minus 1, and it's become 0 and 0. My x star, if I solve above equation, if we solve, this is a necessary condition. The necessary condition showing that your x star is occur, the stationary points, it's occur at one location only, and it's occur at 1/3 and 1/3. x1 equal to 1/3 and x2 equal to 1/3. Okay. We perform the second derivative, finding the Hessian matrix. And luckily, because the order of this polynomial equation is order 2, therefore the Hessians become a constant. And this Hessian constant matrix Hessian is 2, 1, 1, 2. As you can see, leading principle minor is plus 2 and plus t. Both of them are positive number. Therefore, your Hessian is the positive definite for sure, right? And the positive definite and hinge x star is global. Actually, the positive definite is not guaranteed the global minimum. Let me try to explain a little bit. This one maybe my conclusion is too fast. You see this? Local. Remember your function Hessian. Sometimes Hessian is not a constant. For example, in general case, maybe your Hessian evaluate at x star can be something like this, maybe 2x1 plus x2 squared. It can be something like this, right? Can be 1, can be 2x1, can be x2, something like this. In general case, you can expect your Hessian matrix evaluate at the x star, okay? This is a Hessian x, not x star, okay. The Hessians can be a general form like this, right? Just the function, a matrix that contain the parameter x1 and x2 as the unknown. So when I calculate Hessian and evaluate at x star, I will introduce x1 and x2 equal to 1/3, 1/3 in 2. And then my Hessians become a constant matrix. after I introduce x star, the Hessians become a constant. But in general form, the Hessian can be a function of x. That is, in general, it's like that. Therefore, the evaluation of the stationary point using the sufficient condition at the x star, is just the local information. Remember the Taylor series, right? We prove the sufficient condition for the single variable case by using what? By using the movement of the original location extra to the left and to the right hand side a little bit and see whether we're going down or we're going up. If I go allow myself a little bit, and what I feel is I climbing up the hill. If I feel like this, no matter I go to the left, I go to the right, or I go with the 45 degree, I can make a conclusion like this point, x star is the minimum point. But the conclusion is made by considering the surrounding of the x star only. I cannot go further 1 kilometer away. I just go maybe 1 centimeter, 2 centimeter, allow myself and feeling whether I'm climbing up the hill or not. Therefore, the conclusion when we're talking about the positive definite, you are considering the local information only. Local information allow x star. So your conclusion can be made only the local minimum or local maximum. You can say only local maximum, local minimum, as it is in number 1, number 2, and number 3. But why in this example? In this example, I can say global minimum. Why don't I keep saying local minimum? Local minimum, strictly speaking, local minimum is correct, always correct. Because I check the positive definite, mean I check surrounding of myself at allow x star, and I found it is the positive definite. This is the local minimum. But why? I can say global. This is because of what? Because of the convexity. Actually, the conclusion about the positive definite can make the global minimum only. But if you say something more than that, you said your function f is the convexity, right? It's a convex function. Then you can go to the conclusion like this. Because when we say convexity or concavity, we don't look at the extra location only, right? We look at the whole set, at the whole function. We look at the whole function f and found that the second derivative or the curvature or the leading principal minors are convexity. If it's like that, you can make the conclusion about the global minimum or maximum. Okay? Hope you understand the difference about the local and global, about the positive definition of the Hessians and the convexity. That's why people love convexity, people love concavity, because you don't need to go one more step. If your objective function is a convexity, you apply the necessary condition, you obtain only one candidate, one stationary point. And when you check that stationary point gonna be a global minimum, automatically global minimum. But if your objective function, you cannot guarantee that is the convexity. It's not a convex function, for example. Okay, I have to apply the stationary necessary condition, and I obtain stationary points. Maybe I obtain 100 of them, not only one stationary points. Maybe I obtain 10, I obtain 20 stationary points altogether. And what I have to do next is to apply the sufficient condition. When I apply the sufficient condition, I have to check 20 times. I have to check every point, every stationary point, whether it's the local minimum or local maximum. And the conclusion, I have to look at the Hessians, evaluate at the X star, each X star, and proving that that location and that particular X star return me a positive definite matrix or not. If it's return a positive definite matrix, I would say that X star will return me the local minimum point. I can say only local minimum. I cannot say global for such kind of problems. Okay, that's why people love convexity and concavity, because it's easy, it's guaranteed global. Look at one more example. Okay, let me finish this one before. Okay, this one is very easy. Let me go very fast, just 1 minute, and then we can have the discussion a little bit before I stop the discussion today. Okay, if the plant is capable to produce 3 items of maybe stuff or goods to sell to people, each item is stored temporarily in the warehouse. Storage cost proportion to the square of the amount of the amount produced. Find the maximum profit of the production. In other words, I would like to find what would I produce? What would be the production of my factory to get the maximum profit? If I have the storage cost like this, if I have the selling price like that, and the cost of the labor, the cost of the materials, everything, include everything, is like this. Okay, so the profit is well defined as the f of x like this. This is just the, I think this is the selling price. Selling price. Assume that you produce the item number 1 with x1. Item number 2, the amount is x2, and number 3 is x3. Okay, and this is about the cost. You subtract the cost and you subtract the storage. This is the storage cost. Okay, selling price, subtract cost, subtract storage cost is the profit. I would like to maximize this f of x, and I perform the gradient, and I found something like this. Set this necessary condition equal to 0, and I found that my x star stationary point is happen at only one location. That is x star equal to 7,000, 4,000, and 4,000 respectively for x1, x2, and x3. Introduce this one to the Hessian. I found the Hessian become a constant matrix. And this is equal to minus 001, minus 002, and minus 0015 along the diagonal of the Hessian matrix. And it found that the leading principal minor follow the rule of minus 1 power k, right? And is equal to minus for the first, and positive for the second, and minus for the third. And this is the something like a how do you say, concave function. Am I correct? That's why I would say this one looking at leading principal minor, even though Hessian can be said to be a negative definite, but in fact, this leading principal minor also guarantee that the function is a concave function, and that's why the X star is the global maximum. So if you want to get the maximum profit of your production, you have to produce X1 with the 7,000 number, right? X2 4,000 and XT 4,000, something like this. Okay, I would like to stop here because the time is already 10:40 and left this maybe 5 minutes for you if you have the question so far. This is the time of discussion if you have the questions. Okay, any questions? No? If you don't have any questions, let use we have the live group, right? So let us use the live group to share the idea and discuss about the subject. If you find that there is some thing that is quite confused or not clearly understand, you can ask me to the live group and I try to address or answer every question you post. Okay. And one more thing that's just in the chat, I found some of you saying that the internet has a problem and you cannot send the quiz to me. Okay, keep in mind that you have to prepare yourself ready for the lesson. Every class we have the Zoom meeting together, so that if I quiz you, you can, how to say, connect to the Padlet and provide me the answer. And for one of you, maybe you don't have a really good internet connection for some day. Don't be worried so much because I will keep asking you a quiz every time, every lecture or every meeting. I will keep asking you a quiz so that you can have to have a very good score, I think. For example, if we have like a 10 quiz in total, I might use only 7 of them, the best 7 of you to compute the score of the quiz so that you can have a very, very good quiz score for everyone. Okay, if you don't have any questions, I would like to stop here for today's discussion and hope to see you next week, okay? Monday morning, 9 o'clock, we will meet again. Okay, thank you and goodbye for today.
Thank you, Ajahn.
Thank you.
Ajan.
Have a nice day.
Thanks. You too.